Syllabus. How are we doing on syllabus? Coming down? White packet, syllabus? Who does not have a syllabus? Where's the stack of the syllabus? Could please make sure that it gets passed around each way and not just in somewhere? Everybody's got green?
Can you give the green to the side?
Okay. Once it comes this side, we need to make sure it goes to the other side, guys. We go boom, 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 in here. Should not be difficult. One other thing. As you're reading the syllabus, you need to arrive at 5 till 8. Okay? Otherwise, you're late for me. You don't want to be walking in at 8 o'clock. There's no way you can be prepared to learn anything by walking in at last minute. Everybody agree? Okay? Basically, a little bit of traffic, you're late. You need to plan ahead. You need to think to yourself, if I'm not here by 7:50, 7:55, I'm late. Give you a couple of minutes just in case something happens. We need to be settled in, and we will be going at 8 a.m. If you come in late, you will not get handouts, etc., etc. Okay, syllabus. I assume everybody has one. Here we go. Information, it's all there. Textbooks. A lot of this was in the emails I've sent. If you've not been receiving the emails, please let me know. I expect you to read. Okay? I expect you to read the syllabus. All the information is there. The required textbook. One thing about the textbook is I'll let you use any textbook you would like. If you have some type of old textbook, it probably is going to be suitable. Textbook of record is one by Klein. It's sold, a paperback version is sold in the bookstore. There are many other good textbooks. Here's one by Smith. We used to actually use Smith here. I do this to save you some money. Maybe you have a friend who took organic chemistry someplace and they gave you your book. Fine. All books are pretty much the same in terms of content. There will be topics in the Klein book that are not in the Klein book that we'll be covering. I'll say it, we will be covering topics that are not in the Klein book. So maybe those topics are in the Smith book that you have to have from your friend. Okay? Your textbook is your resource, critical resource for reading about the material, getting your background information for working basic problems, including in-chapter problems and end-of-chapter problems. You must have the solutions manual that goes with your textbook. Otherwise, you will not know the answers to the problems that are in the textbook. Make sense? You must be working problems because you must convince yourself that you're ready to go for test day and quiz day. How else can you do that other than work problems and to make sure that you know what you're doing? If you do not work problems in your textbook and make good use of your textbook, you probably will not pass this course. Okay? I will give you a number of recommendations. It's up to you to take my recommendations, should you choose so. Okay, there are a number of recommendations in the syllabus. All the information is here, including important dates at the bottom, course overview, grading, some very important procedural information, miscellaneous comments and information. This page here is our daily outline. Today we'll be starting with low structures, etc., functional groups. On the right is your lab, either Thursday or Friday. What are we doing in lab this week? Check in, and then we'll have lecture. I call that a lab lecture. That will be downstairs in some room. We'll determine which room. Check-in instructions are in the lab manual. I have created my own workbook/lab manual. The first half is workbook, second half is the lab manual. As said in the email, this is only available upstairs in the chemistry physics department, $15 cash only. That just covers the binding materials and a little bit of labor. Feed the hungry students to help put them together. Most of this in here used to be handouts, even more handouts. Okay, I think you will find this to be a very organized resource for you. Okay, it has a table of contents. Please make sure you know what's in here. Basically, the workbook portion is practice problems, and there's also answer key portion in here. Also in here for the lab are your lab requirements and guidelines, safety information, guidelines for reports, guidelines for working in the lab, guidelines for notebooks, etc., etc. For me, I don't like to tell you much. I like to write it down and expect you to read it. Because if it's written down, you can read it a million times. And you should. If I tell you, what do you think? No, I don't do that. I write it down and expect you to read. Okay? If anything is ever unclear, please let me know. All right? What I particularly don't like is when you ask questions that are clearly like on page 1 in bold. That indicates that you have clearly not even read one time. Okay? Learning how to read directions to me is very critical. You guys need to be working on that. In general, most students tend to be a little lacking in that area. Please see that as something that you should work on because it will benefit you moving forward. All right? Also asking questions. You need to work on asking questions. Asking questions requires that you think about the material. How well am I doing? What do I need work on? And then from there, you are forming questions. If you're not forming questions, I worry about your study habits and how much you're invested in the course. And then I worry how you're going to do on tests, et cetera, et cetera. So a good barometer for me is, well, what type of questions are you asking? Okay. So here's your lab schedule each day. In the lab manual, there's lots of labs. We're not doing them all. They're not in this order. This is what we're doing each week. Had students show up and prepared to do the wrong lab because they did not follow this here. That's the schedule. Okay. Requirements for lab check-in are in the lab manual, so you need to get the lab manual. And you need to read the requirements. And at 2:30 each day, we'll check in. Okay? And when we come to check in, basically I'll say, okay guys, check in. You already have the requirements and guidelines. My background is in medicinal chemistry. That's drug development, organic chemistry related to drug development. Majority of drugs are organic compounds. Here's some common examples. Many of you have heard of these. You've actually probably taken some of these, like Tylenol. All small organic molecules. At the beginning of the course, we will be focusing on the architecture of organic compounds. Okay? Structure, functional groups, hybridization, lone pairs, geometry, bond angles, bond strengths. Okay? Line bond structures. Okay? We don't show carbons, we show these points, vertices. And so dealing with line bond structures will be something we need to quickly get used to. So a number of drugs, including a billion-dollar drug, Lipitor, some stereochemistry, beautiful molecule, right? On the back is a little bit more detailed chemistry of ibuprofen. Top portion, these are some types of questions that you should hopefully be able to answer after taking this course or along the way. Okay? At the bottom are some more advanced questions that you may then see as you move on to maybe classes in medicine or pharmacology, something like that. So, we have prereqs for this course, which are Gen Chem 1 and 2. All right? Lots of material that you should be familiar with. And I will not reteach you that material here. There's expectations that you use that material. Prereqs, yeah? Okay. I suggest you keep your Gen Chem book handy and always review topics from Gen Chem so you can take that language there and then mix it with the new language and see how they match up. Okay? That helps you say, yeah, I understand that because that's what we did here, but it's just presented a little bit different. Okay? So it helps you see what you really know. Okay? You got to build your knowledge. That's what prereqs are about. But this course is also a prereq to other courses, Organic 2. Okay? But from there, you have to have Organic 1, Organic 2 to go into biochemistry. And then like pharmacology or any other advanced courses that have anything to do with organic chemistry. All right? So, on Friday, the first thing I'll do is ask you if there's any questions about the syllabus. All right? Any questions today, though? Yes?
Do you have any extra? I didn't receive it. Thank you.
Also on Friday, you should be turning in your pre-course questionnaire. Send in the emails, yeah? We'll collect that on Friday morning. Yes?
Would there have to be a standardized test we would have to take at the end of the semester? A standardized exam we would have. Is there a standardized exam we would have to take at the end?
I don't give us standardized. I give my own exam in this course. It's in the syllabus. Yeah. Some instructors do give a standardized in Organic 1. I only give one in Organic 2. And most everybody does in Organic 2. Only very recently has the one in Organic 1 become available, but I don't use it. Okay, we need to get off to a good start today. Other handouts. The green is our outline. Okay. We'll often have outlines. This is what we will start with. Okay. This is also what I go by with organization for you, but it's also my organization. So we're beginning with what? Roman number 1, right? Which is what? Review of atomic structure. And any organic chemistry book out there is going to have a little review of atomic structure. Yeah? Uh-huh.
The green or the yellow? Thank you.
The white I just call a handout. It's going to be miscellaneous things that we'll be referring to. You didn't get one?
Yeah.
Which ones do you need?
All of them.
And the yellow is a page that I call a DQ, Daily Questions. This is daily questions. We got about 10 or 11 days before test 1. Okay. With each day, we'll make certain progress. All right, covered certain material. These are sort of in order for day by day. So it can give us sort of, as a class, maybe a couple of questions to start the initial focus on. All right. Should always be prepared to see these possibly work in class. As opposed to you come in and I work some random question that you never had looked at yet. Couldn't expect you to. You didn't know how it was going to work. But you do know what I might work, because I gave you each day a question that everybody should be minimally prepared for. All right? That way I won't be working some surprise question, although we will do a number of surprises. Again, it's some organization. Okay, this is how we're progressing through test 1 material. So after the first day or two, it's not exactly in order, but after the first day or two, you should be able to do question 1. And after day 2 or 3, okay? Guess what? If we've done 5 days and you can't do any of these questions, that should tell you that you need to make some study changes to your study habits, etc. These are also the types of questions you'll see on the test. General type of format, etc. Okay. Any questions while I'm getting things together here? Again, I think you'll be quite amazed as you go along when you get to through this course and through Organic 2. Lot ahead. But we take it one day at a time, yeah? Okay. Also, what we present each day is very critical because we build upon it. Very different from Gen Chem. In Gen Chem, you study a chapter, and then the next chapter is totally different, right? You just forget about the previous stuff, right? You cannot do that in organic chemistry. If you don't learn the stuff in chapter 1 and 2, you're not going to be able to do the stuff in chapter 4 and 5 and on and on. All right? So it really builds. Day 1. All right? And so you have to think, what did I get out of day 1? What's important for day 1? All right? And then day 2 will be coming right behind. All right, let's get going. There'll be plenty more to say as we move along. We'll see about your questions about the syllabus on Friday. Check in on Thursday and Friday, yeah? 2:30, instructions in the lab manual. We'll have some lecture after we check in. The requirements for being in lab. Okay, review of atomic structure. Let's see. Organic chemistry. Chemistry of cool stuff. What's cool stuff? Cool stuff, right? Pretty cool. I think that's Dutch for what element? Carbon. Yeah, Dutch for carbon. Cool stuff. They know it's cool stuff. They call it cool stuff. Chemistry of carbon, right? That's overly simplistic. Chemistry of carbon. Let's start with carbon. Carbon. What's the atomic number of carbon? 6. Okay. 6. Yeah. What type of mass number can we give carbon?
12.
Okay, we can maybe say carbon 12. How many protons would this isotope have? Number of protons equals 6. Number of neutrons? 6. Number of electrons? 6. 6. Yes. Assuming it's neutral for the electrons. Of course, it can be an ion. I mean, the number of electrons can vary. So we'll consider it neutral. Where are these guys found at? The nucleus? Electrons are not in the nucleus. Electrons are on the outside, the periphery of the atom, right? Okay. The skin of the atom. And the electrons are what's going to be reacting for us. We will not be doing any nuclear chemistry. We will not be changing number of protons and neutrons. Okay? Only electrons for typical reactivity. But can we have other, what if we have something like this? By the way, do I need to draw that 6? No, the mere fact that I said carbon is 6. Every carbon is 6, right? So usually that number is not shown. What is this? Called C13. You call that C12, but C12 is just common, yeah? C13, what's the numbers here? Number of protons? 6. Number of neutrons? 7. Number of electrons? 6, assuming it's neutral, right? What varied here? Number of neutrons? Yeah? 6 and 7 is 13. That's where that number comes from. Yeah? What's the relationship between these two? Cousins? Brothers? What do we call them? Isotopes, yeah. They vary by what? Number of neutrons, right? You know all this. Are there any other isotopes of carbon? Yes, there's many isotopes of carbon. These are the only 2 natural ones. No, I'm sorry, there's a third one. I've got to put up the third one. 14. Carbon 14 equals what? 6. What is this? 8, and this is 6, assuming it's neutral. Yes, these are the 3 natural isotopes of carbon. What is the natural percentage of each? What percent of the carbons in your body are carbon 12? You may be looking at the periodic table, it doesn't say it directly. What is this number, 12.0108? Average of the isotopes. But it's 12.01. Makes you think that 12 is very major, because it's not that close to 14. It's pretty much 12. That makes you believe that this is the major one. In fact, it is. This is 99%. I'll round this off. You guys familiar with sig figs? Good, because sig figs remain important beyond Gen Chem. That's not one of those topics you just learn and then never do again. Right? Sig figs are very important. Everybody agree with me? Good. We've had that discussion, right? Okay. 1% here. 1% is carbon 14 in your body. Heather?
I'm not sure.
Well, 99 and 1. What does that tell you? Yeah. I mean, 0 based on, I rounded off. I'm only using one limited number of sig figs. It's in the noise. It's like 0.01%. I mean, it's something very small. If you round off, you lose that significance. Right? You know all that, sig figs, right? Yeah. Trace amount, we can call it. Yeah. The trace amount is very important. Of these 3 natural ones, that one's radioactive. And this is the one where when the dinosaur dies, it starts breathing in, it stops exhaling CO2 or whatnot, and so this amount stays constant, and then it starts decaying, and you can tell how long the dinosaur's been dead, and we call that carbon dating, right? Radioactive. Trace amount, though. You can also have carbon 11 and 10. You look on Wikipedia, isotopes of carbon, it'll show them all. The other ones, though, are man-made. You know you can make isotopes? You can make them. These occur naturally, but you can also make some. Chemists can make them. Chemists can do a lot of things. They actually make an isotope of fluorine over here on Central Avenue. Use it down at the hospital for PET imaging. Okay? These are the 3 natural ones, though. Okay. Electron configuration. How many electrons have we got here? All these are 6. Let's see. Remember electron configuration? What do we got? 1s, is that right? I haven't had Gen Chem in a long time. What's next? How many we got there? 1? 2s? What is that? 1? What's next? 2p? What do we got? Ground state here. Okay? I don't always write everything ground state. I don't have that much ink. But guess what? I mean, it's stated here. I also have the video when you look back and you review what went on today. Okay. Electrons, fill them in, off-ball principle, Hund's principle, Pauli exclusion principle, all that, right? What we got? 1, 2, 3, 4, 5, 6. Yeah? Ground state. What do you call this second shell in this case? The most outer shell. Yeah, those are your valence electrons. Valence electrons. How many valence electrons does carbon have? 4. Very important. Valence is the shell that's going to participate in bonding. Yeah? How many electrons does carbon need to fill the outer shell? 4. It needs 4. And then it will have 8 in the outer shell there. Of course, it will be hybridized, and we will talk plenty about that. But once it achieves 8, then it achieves the configuration of what? Neon, right? Valence of carbon is 4. Ground state. There's lots here that you know, right? And when we get into hybridization, we'll start with that and all that you know, and we'll build upon it. Types of orbitals. What's an s orbital look like? Yes, spherical, right? Okay, like a volleyball, with the nucleus right in the middle of the volleyball, right? What's a p orbital look like? There's the nucleus. We have a dumbbell-shaped p orbital, where at the nucleus there's actually no electron density. Yeah? All this is just review, right? Types of orbitals. Okay? When we get to hybridization, we'll be mixing these orbitals. You did that, yeah? You did some hybridization in Gen Chem? Okay? We'll build upon that. Did we cover everything under Roman numeral 1? Let's look back here. We talked about isotopes. Let me show you a little bit. I'll try to show you some applications along the way. The back, flip side, the green. This compound here is used to image the brain when looking for Alzheimer's disease. Alzheimer's, the brain develops these beta amyloid plaques, which cause lots of trouble. Okay? How do you know if the patient has that in there? You're not going to cut open the brain and look. You're going to like imaging these days, right? Okay? PET imaging, and a compound that is used for PET imaging to give the image is shown right here. All right? Small organic molecule. Number of carbons, a couple of oxygen, sulfur, a couple of nitrogens. But on this nitrogen, there's a methyl group combined to this carbon. But the carbon is carbon 11. It's an artificial isotope, not natural. It has to be man-made. It can be. All right? But carbon 11 is a positron emitter. That's how it decays. And that can be used to create an image. All right? This compound is called Pittsburgh Compound B because it was developed at the University of Pittsburgh, I believe, or a hospital in Pittsburgh. All right? I don't know what happened to compound A, but B became the big one. The best one. B for best, all right. You can find that compound on Wikipedia and find so much more information about it. That's black and white. I don't know that I have a colored version. But the color version is here, can be found on Wikipedia. Basically, this is a type of image. Normal brain on the right, I believe. Yeah, in this case, yeah. Control Alzheimer's disease. The red, not good. All right. But that compound is what led to this imaging. okay? Importance of organic chemistry, organic compounds, and of what we can do as chemists and scientists. The other on the back is, so that's an isotope of carbon. Isotopes, though, are of hydrogen. Very important. We'll see these along the way a little bit. Isotope of hydrogen, that's what this page discusses. The isotopes of hydrogen actually have names. All right? H2. H2 is called deuterium. Goes by D. H3 is tritium. Tritium is actually radioactive. They used to deal with it out at the Savannah Riverside. Today, a lot of, more and more drugs, I don't say a lot, but drugs are starting to have deuterium incorporated into them. This sort of tries to explain why. The bond strength of the CD is stronger than the CH, and that enhances some of the drug activity in a couple of different ways. You can read this. A lot of these applications I give you, I have to give them to you very quickly because we don't have time. If you want more information, then look it up somewhere or ask me. Okay? But it's the applications that are what's so interesting and important. That's why we're here. To learn to be able to know and understand such like this. All right? We're not here to learn chapter 3 because that's so critical. We're here to be able to take that knowledge and do something with it, right? And understand. Once you understand, then you can be a scholar of the material, but then you can go make other advances, improve upon this. If not you, who? Right? Bonding. Covalent bond. Well, that's the only kind of bond, right? Any other types of bonds? Do what?
Ionic.
Yeah, thanks for that answer. I don't like to call ionics bonds. I would call that a charge attraction or something. Because you guys want to, calling it a bond usually messes you up. Call it a charge attraction. All right? Covalent bonds, definition, etc. Well, sharing of 2 electrons, does that sound right? How many valence electrons does hydrogen have? Or electrons total? 1, right? All right, you know all your periodic trends? How many neutrons does tellurium-128 have? Easy, right? Right. Hydrogen, 1 electron. Well, what do we call something with 1 single electron that's not paired? What do we call something with 1 electron that's not paired? Unpaired electron. Radical. Right? Radicals typically are not stable. Typically we're going to see all electrons paired, either as a bonding pair or a lone pair. Yeah? It's not good. Only 1 electron. H wants another electron so it can become like what? Helium, right? It's just like carbon, except with the first row there's only 2 elements. Why is there only 2 elements here? Well, it's right over here, because if you've only got 1 orbital, you only got 2 electrons, and it's filled with 2. So 1, 2, right? But this can team up with another hydrogen. These 2 can team up, and we can get to something that looks like this, right? And this is now basically this. And this is overly simplistic. Of course it is. All your bonding has been overly simplistic. But you have to understand it to a point. What are we saying here? These 2 nuclei are sharing these 2 electrons between it. Two electrons shared between two nuclei is what? Covalent bond. Okay? And we show a two electron covalent bond with a dash, right? So it's all just simple. But there's a huge amount of science and chemistry in this covalent bond. You can write an entire textbook on this right here. All that goes into bonding. Why do the electrons come together? Shouldn't electrons repel? Well, the answer to that is overly simplistic. But then there's all the math. Basically, this is as far as we're going to go to bonding. All right? Two electrons being shared. But we can do so much more at the simplistic level. Later on, you can go take chemistry 5980, the science behind the chemical bond, and you can spend an entire semester on that right there. We will not do it. But two electron covalent bond. Now the important thing is we can talk about is each hydrogen gets to count as if they own the two electrons. So now this hydrogen nucleus owns the two electrons. All right? And it can become like helium. But then that one owns two. They can both become like helium. There's not 4 electrons there. There's only 2 there. All right. Now sometimes you may also see maybe like the electron density shown here. All right. Lots we can say here. Importantly though, one thing if you haven't sort of caught on in Gen Chem along the way, every time you make a bond, the nucleus gets one more electron. So now with a bond there, this H doesn't have 1, but we say it has 2. Each bond gives you 1 more. Let's move on to carbon, second row. And we're going to do these C, N, O, and F. I'm going to kind of come across the board here, so leave room on your paper to kind of come across. Let's look at carbon. How many valence electrons does carbon have? We've already said it right. 4? Let's put these around. H, I just put 1. Carbon has 4. 1, 2, 3, 4. And with the H's, I wish I had used an X for the second electron, but I didn't. Here I'm going to use X. How many electrons does it need to have a filled octet? 4. Okay, we bring in electron. What if you have this H? Okay, and instead of a dot, let's call it an X. All right. We can bring in the H with its electron and team up an H and a carbon with a 2-electron covalent bond and make a bond here. Well, we can do that 4 times. All right? By the way, with the H, we didn't use this terminology. We ended up with 2 electrons around the hydrogen, right? Common term for that is a duet. Right? Hydrogen wants to achieve a duet to become like helium. On the other hand, carbon wants to achieve an octet, 8. All right? First off, look at the H's. Does each H have the duet? How many electrons does this hydrogen now own in terms of a shared count? 2. Each H is good, making 1 bond. Now it has 2. Okay? Each H is happy, satisfied. How many does carbon own in terms of a shared count? 8. 2, 4, 6, 8. Of course, we can show this molecule usually just with the dashes, yeah? Standard bonding for carbon. 4 bonds, 0 lone pairs. Standard bonding. Standard bonding just comes from the periodic trends of what carbon needs. look though at nitrogen. How many valence electrons does it have? 5, right? 1, 2, 3, 4, 5. We're going to pair one up there. How many bonds does it need to make to get its octet? 3. How many bonds to hydrogen? 3. We can bring in an H, but it's one electron, team it up with one of those nitrogen electrons. And we can get a happy camper like this. Nitrogen now good. First off, H now good. H only makes one bond. That's all it needs to to have a duet, right? Because it only makes one bond, H is always on the periphery of your molecule. H can't be in the middle making multiple bonds, right? We clean this up a little bit. We can have H, 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 and what's here? Lone pair. Lone pair of electrons, or sometimes called a non-bonding pair. I always call it lone pair, or LP. This is standard bonding for nitrogen, because now nitrogen has its octet. 2, 4, 6, 8. 8 electrons around it. Standard bonding for nitrogen is what? 3 bonds, 1 lone pair. Oxygen. How many valence electrons? 1, 2, 3, 4, 5, 6. I'm waiting on the question to come. Hopefully it will. 6. How many bonds does it need to make? 2. We can bring in an H with its 1 electron. Bring in another H with its 1 electron, and we can get a good molecule. H has a duet? Yeah, 1 bond. Yeah, we pretty much don't need to keep repeating that. Is the oxygen good though? One of the primary things of a good bonding arrangement is, does the atom have the octet for the filled outer shell? But for most time that's going to be octet. Does oxygen have an octet? Yes. 2, 4, 6, 8. 8 electrons around. Of course, we can clean this up. We can get something like this with 2 lone pairs, right? Standard bonding for oxygen is shown here. What is it?
2 bonds, 2 lone pairs.
2 bonds, 2 lone pairs. Standard bonding for oxygen. What's standard bonding for sulfur? 2 bonds, 2 lone pairs. What's standard bonding for phosphorus? 3 bonds, 1 lone pair. Because if it's in the same, same group there, it's going to have same bonding. But there is sort of exception. Once you get below the second row, these can have other types of bonding. So phosphorus can't have other types of bonding other than 3 bonds, 1 lone pair. Because this row has what type of orbital that those do not. Third row, right? What type of orbital now comes into play? D orbital, yeah. And with the D orbital, phosphorus can have other types of bonding. But it can also do that standard, just like a nitrogen. And a sulfur or selenium or tellurium can do just like the oxygen here, okay? Where these can't do what the other than those can. What's next after oxygen? Fluorine, number of valence electrons. 7. How many bonds do we need to make? It only needs 1 electron. Bring in a hydrogen. By the way, we don't just bring in hydrogens. We could bring in something else. Don't draw this. Don't write this down. We could bring in a carbon, right? But if we brought in a carbon, not only would have 1 that can team up there, but the carbon would have 3 others, right? And now you gotta have bonds here, and you can build a bigger and bigger structure. But I'm not complicating. I'm just bringing in hydrogen at this point. Because hydrogen only has one, and it's just simple in this. It's here. There you go. What is that? HF. By the way, lone pairs. A lot of times they will not be shown. All right? Out there in the world. You got to know they're there. If we ever do official Lewis structures, they need to be there. It's not correct if we don't. But there's 3 lone pairs here, right? And what's a Lewis structure? A Lewis structure is where you show all the valence electrons either as bonds or lone pairs. Basically your structure. But it's the formal name is a Lewis structure. It calls Gilbert Lewis. He wrote the big, huge book on the nature of the chemical bond. Right? Back almost 100 years ago. Common bonding for, what do we call this group over here, group 7? Halogens. What's common bonding for the halogens? 1 bond, 3 lone pairs? Yeah? Standard bonding. If it ain't standard bonding, you can't see things without standard bonding. I mean, we may see this. You don't always write everything down. You know, sometimes I'm just doing it real quick. We have this structure. Is that standard bonding for oxygen? No. Then 99% of the time, it's going to have a charge. It ain't standard bonding, it's probably going to have a charge. And with Lewis structures, you also need to show correct charge, or your structure is not correct. Anybody know the charge of this guy? Why don't you show that? Make sure you have it drawn. Charge of this oxygen. Anybody got charge of the oxygen?
+1.
Think about it. Let's see what we can do to finish up here. Lewis structures. We want to avoid radicals unless absolutely necessary. Occasionally we'll see radicals. I talked about silicon, phosphorus, sulfur. These guys can expand their octets. Okay? And there's a page in one of the handouts about that. Bringing in the d orbitals. And so you'll see a phosphorus that ain't like the nitrogen. It's atypical. It's okay. But you need to be a little bit familiar with that. Structures with single bonds. CH4O. All right? I'm going to start trying to put structures together. CH4O. All right. You stay in class. We'll end at a certain point. What I expect of you is for next time, you be looking ahead. Okay? When it doesn't always say homework, but hopefully it's pretty intuitive that you should be trying to put together these structures. This is what you need to do to prepare for the next time. That way, when I present it to you, you will have thought about it, you'll have thought about what difficulties I'm having, etc., etc. Then you'll be able to get more out of the lecture. All right? So we'll be moving ahead. There's your outline. Everything's coming. Functional groups. Yes, you can start looking at them. They're in the handout. Okay. See some of you tomorrow for lab check-in. Thursday, yeah. Thursday lab. And on Friday, you're turning in your pre-course questionnaire. Have a good day, guys.